My name is Fangfei Lan, a PhD student from the Scientific Computing and Imaging Institute at the University of Utah. I will be presenting our STAR report, Visualization in Astrophysics, Developing New Methods, Discovering Our Universe, and Educating the Earth. This is joint work with my fellow graduate student, Michael Young, astronomers Lauren Anderson and Juna Kohlmeyer, visualization experts Anders Jennerman, Alexander Bach, Angus Forbes, and Michelle Borkin, and my advisor, Bei Wang. First of all, let me pose the question, why do we care about visualization in astrophysics? The answer lies in the path of astronomy. From an illustration of the Ptolemaic geocentric system by a Portuguese cosmographer and cartographer in the 16th century, to Galileo's sketch of Jupiter's moons in the 17th century, to nowadays a wavelength image of a molecular cloud, our observations and captures of the supermassive black hole, a reconstruction of the Milky Way, and a 3D printed model of a nebula. Astronomy has evolved dramatically. However, visualization has always played a crucial role in astronomical discoveries. Astrophysics is inherently visual, and modern astronomers are recording an increasing amount of information. These data present opportunities to make enormous strides in discovering more about our universe and state-of-the-art visualization methodologies. This survey aims to become a reference point for building connections and collaborations between two communities: data-rich but technique-hungry astronomers and data-hungry but technique-rich visualization experts. This STAR report serves as a starting point to bridge the knowledge gap between these communities. We want to help visualization experts better understand the needs and opportunities in astronomical visualization and provide a mechanism for astronomers to learn more about cutting-edge methods and research in visualization as applied to astronomy. We surveyed 80+ papers from the past decade in the fields of astronomy and visualization that contain strong visualization components for astronomical data, and classified them based on 3 dimensions of categories. In this talk, I will first introduce our primary, secondary, and tertiary categories, and discuss representative and unique examples based on the primary categories. Then I will present the challenges and opportunities in the field of AstroVis that we identified through this process. Finally, I will introduce an additional navigation tool we developed to complement our categorization. Our classification of the surveyed papers is guided primarily by a set of data analysis tasks, secondarily by a set of visualization techniques, and finally by a set of topical areas in astronomy. We view these 3 categories as being on equal footing and not necessarily hierarchical. Instead, they're considered orthogonal dimensions and provide complementary viewpoints. We organize the literature according to these 3 categories to provide a means of navigation from task-driven, technique-driven, and topic-driven perspectives. We identify 5 primary categories of approaches based on data analysis tasks. They are data wrangling, which transforms astronomy data into formats that are appropriate for general-purpose visualization tools. Data exploration, where users explore a dataset in an unstructured way to discover patterns. Feature identification, which visually guides the identification and extraction of features of interest. Object reconstruction, which provides an informative visual representation of an astronomical object. And education and outreach, where astronomical data and data products are made accessible to the general public. Our secondary categories are based on visualization techniques employed for astronomical data, and they include 2D and 3D plots, such as histograms, scatter plots, and pie charts, 2D images that use image processing techniques to generate discoveries of astronomy data, 3D rendering that creates a representation of 3D volumetric data, interactive visualization that includes techniques such as linked views, detail on demand, visual filtering and querying, dimensionality reduction that transforms data from a high dimension into a low dimensional space. Uncertainty visualization that communicates the uncertainties in astronomical data that arise due to the randomness in data acquisition and processing, and new display platforms such as data physicalization and virtual reality. Our tertiary categories are based upon a list of topics from the NSF Astronomy and Astrophysics Directorate. They are extragalactic, galactic, planetary, and solar astronomy. These categories are used as a cross-reference for an astrophysics audience. In addition, we labeled each paper with the tags simulated and observational astronomical data. We present the surveyed papers mainly based on our primary categories. Now let's dive into the first category, data wrangling. Data wrangling is the process of transforming raw data into forms that more effectively support downstream analysis. This process is an important step for astronomy visualization because raw simulation or observational data requires significant wrangling into a suitable form for visualization tasks. This table presents an overview of our categorization of data wrangling papers. We see that for our secondary category, data wrangling research emphasizes 3D rendering and interactive visualization techniques. Many of the papers placed in this category focus on transforming raw astrophysical data cubes into suitable data formats that can be ingested into open-source graphics and visualization tools, such as Blender and Houdini. Many of these techniques can be applied to multiple topical areas in astronomy, and both simulated and observational data. AstroBlend, introduced by Neyman, is an excellent example. The software extends the 3D graphics software Blender, making it possible to import and display various types of astronomical data interactively. It is an open-source Python library that uses YT, a software that analyzes and visualizes volumetric data, to support the data loading and visualization process. Borkiewicz et al. Presented a method for creating cinematic visualization and time-evolving representations of astronomy data. They introduced a detailed pipeline of importing nested, multi-resolution, adaptive mesh refinement data into the 3D procedural animation software, Houdini. Their goal was to create astronomy visualizations that are both educational and aesthetically pleasing. There are also efforts on advocating for certain file formats that are more suitable for visualization. Bolt et al. Proposed to improve the access and publication of astronomy data visualization using 3D diagrams based on the X3D file format, called X3D pathways. They advocate for the X3D file format because it lies in the center of a variety of display formats such as movies and animations, 3D printing, interactive HTML, and PDF documents. X3D pathway is file format dependent instead of software dependent, making it less likely to be affected by rapid technological evolution. Now let's take a look at our second category of data analysis tasks, data exploration. Data exploration facilitates the unstructured investigation of dataset in order to discover patterns of interest and formulate hypotheses. We present an overview of our categorization of data exploration papers in this table. Similar to data wrangling, data exploration tools span all 4 of astronomy topical areas and can be applied to both simulated and observational data. Most works in this section use 2D and 3D plotting to accompany the 3D rendering and interactive visualization in order to provide more statistical analysis functionalities. I would like to point out that we did not see any research work in the data exploration section with a component of uncertainty visualization. Although it is a bit surprising, this presents great research opportunities for the future. Some of the tools were developed with specific use cases in mind, such as ESA Sky. ESA Sky is a web application designed for the exploration of multi-wavelength skies and the visualization of the coverage of the ESA astronomy missions. The video shows the process of loading multiple skies and visualizing data of the ESA mission. There are also tools that support a large variety of tasks for astronomy datasets such as OpenSpace and Gaia Sky. OpenSpace has already demonstrated its success at supporting educational and outreach activities in museums and in planetariums. It is also constantly evolving to facilitate scientific research. It exhibits a number of novel features, including globe browsing, which displays the planetary surface textures, and an atmospheric model that visualizes planetary surfaces. As new display platforms gain popularity, Vo et al. Presented N-Cube, a visualization software that can be used on a single desktop as well as in the Cave 2 immersive virtual reality display environment. A unique feature of N-Cube is its VR capabilities for comparative visualization. It exploits the Monash Cave 2's 4 rows by 20 columns configuration and displays on all 80 screens simultaneously. Each screen is selectable and interactive. Here's a number of selected screens from the visualization of different galaxy morphologies. Since its introduction, TopCat has been widely used to view, analyze, and edit tabular data in the astronomy community. Over the past decade, the developers of TopCat have continued to improve its capabilities, with a number of innovations in 2D and 3D plotting. One important new feature is a hybrid scatterplot/density map that enables users to navigate interactively between the high-density and low-density regions without changing plot types. For our third and fourth categories, we have feature identification and object reconstruction. Feature generally means a measurable piece of data that can be used for analysis. We recognize that objects may be considered features with sharp or discontinuous contrasts in a dimension of scientific interest. Whether a specific aspect of a dataset is considered an object or feature depends on the scientific question posed. We separate these two categories to be compatible with literature, but we envision a future where these entities are recognized as a continuum. Now let's dive into the details of feature identification. The detection of features in an astrophysical data stream is important since many interesting phenomena are diffuse or observed with a low signal-to-noise ratio, and distinguishing between signal and noise is critical. In this overview table, we see a wider variety of visualization techniques used in papers of this category than in data wrangling and data exploration, including more examples of 2D images and dimensionality reduction. Although feature identification applies to both simulated and observational data, the majority of papers in this section focus on dark matter simulations and the cosmic web, which are extragalactic astronomical data. In particular, voids, filaments, and dark matter halos. Sheng et al. Built an interactive visual analysis system that focuses on exploring the evolutionary histories of halos. They proposed a unique particle trace path graph, which encodes the evolution history of selected particles, indicating the formation of a dark matter halo. Preston et al. Aimed to increase the efficiency and interactions in studying the evolution of halos described by merger trees. They used linked views to allow interactions between three views: the 3D rendering view, merger tree view, and quantitative analysis view. An important feature of the system is that it enables simultaneous exploration of heterogeneous cosmology data. Felix uses a topology-based framework to identify cosmological features. It focuses on extracting the filamentary structures in a dark matter simulation. The filaments are displayed in the orange tubes, and the three figures are generated from adjusting the query parameters. It incorporates a visual exploration component by allowing the users to interactively query for specific density ranges. Tampaka et al. Applied deep learning to estimate galaxy cluster masses from Chandramak, which are simulated low-resolution X-ray images. They used a relatively simple convolutional neural network, but their main innovation is the visual interpretation of the CNN, using an approach inspired by Google's Deep Dream. Comparing the left and right image, we see that in the right image, the CNN misclassifies the cluster core above and to the right of the true cluster core, which lies in the center of the image. Their work illustrates the utility of interpreting machine learning black boxes with visualization, since it provides physical reasoning to predicted features. We now move on to the object reconstruction category. Object reconstruction provides informative visual representation of astronomical objects. From this overview table, we see that research works in this section have a strong emphasis on observational data and the use of 3D rendering as the main visualization technique. I do want to point out that there are two works in this category that built uncertainty visualization into their reconstruction pipeline. This is often considered difficult for astronomical data. We'll discuss more about it in the challenges section. Now let us look at some examples in the object reconstruction category. Using the positions and distances of thousands of classical Cepheid variable stars obtained through observations and accounting of the stars' pulsating periods, Scoren et al. Constructed a 3D map of the Milky Way galaxy. They used 2,341 such stars to sketch the Milky Way galaxy and observed the warped shape of the galactic disk. Polyform is an interactive visualization and filament reconstruction tool that enables the investigation of cosmological datasets. In contrast to filament extraction tools such as Felix, Polyform is able to reconstruct the cosmic web from galaxy observations. Its fast computational simulation method is inspired by the foraging behavior of a type of slime mold. Simulation data often possess inherent uncertainty because of manual errors and measurement inaccuracies. Bach et al. Proposed a multi-view visualization system that uses uncertainty visualization to verify simulation results of the Sun's corona mass ejections. The left figure shows the ensemble view of a number of simulations and its associated uncertainties. The system also integrated a 3D spatial view of the simulations shown in the right image. Finally, we introduce our last category, education and outreach. In an ongoing paradigm shift in scientific outreach, technological advances are enabling data-driven and interactive exploration to be possible in public environments such as museums and science centers, increasing their availability to the general public. Here we present the overview table. We see an overwhelming popularity of 3D rendering and interactive visualization techniques used in this section's works. These techniques are often used to create large-scale immersive environments for planetarium dome theaters. More recently, there has been a greater focus on interactive methods where the user becomes part of the exploration. New display platforms, such as augmented reality, virtual reality, and 3D printing, are emerging and exciting mechanisms for science communication and broad dissemination. Here I present an example of an interactive presentation in a large-scale immersive environment to the general public. It is an image taken at the Brilliant Minds conference. Software such as OpenSpace and Worldwide Telescope are among the most popular tools that are used to create scientifically informative and aesthetically pleasing visualizations for these immersive environments. Worldwide Telescope is a virtual observatory for the public to share and view data from major observatories and telescopes. The open source software provides the capability to visualize the solar system and stars and show observational material in context. Virtual reality and augmented reality are also used in museums and science centers. Arkin et al. Developed a 3D VR and AR program to visualize the Cassiopeia A supernova remnant, giving users the experience of walking inside the remains of a stellar explosion. Madhur presented a case study using 3D printing to visualize the Eta Carina Homunculus Nebula. The 3D models not only facilitate research discoveries, but also help communicate scientific discoveries to non-astronomers, especially to the visually impaired. In addition to a taxonomy of existing approaches that utilize visualization to study astronomical data, our contribution includes a summary of the current challenges and opportunities in visualization for astronomy. The major challenges are data volume and diversity, interactive visualization and intelligent querying, uncertainty visualization, time series data visualization and analysis, machine learning, and further advancement in education and outreach. We review 3 of the representative ones here. As we've seen from this presentation, uncertainty visualization in astronomy remains largely unexplored. We present here the 2 examples we found from the object reconstruction section. Errors and uncertainties are often introduced due to data acquisition, transformation, and visualization. But applying uncertainty visualization to 3D astronomy data is challenging because we lack the techniques to deal with sparse and faraway samples and their large error cones. However, the potential exists to display uncertainty in a localized object or regions of interest, and that potential must be developed further. Most of the current time series data visualizations are built to display halo evolution as we presented here. The technique often used is the merger tree visualization. In general, time series data visualization can also be helpful when tracking star movements. However, little effort has been expended in this regard, with Gaia Sky being the only example, to the best of our knowledge. Time-dependent visualization, in particular, the interplay between spatial and temporal dimensions, will be crucial as more time series astronomy data become available in the near future. Many astronomers voice their desires as well as concerns about using machine learning techniques, and in particular, deep learning, in the astrophysics discovery process, mostly surrounding the interpretability of black box ML models. Most works we've seen so far have used convolutional neural networks for classification tasks. We believe that combining visualization with machine learning models has the potential to make the results more accessible than classical interpretations. A good starting point to obtain interpretability is to combine visualization with models that are inherently interpretable in studying astronomical data, such as linear regression, decision tree, and naive Bayes. Topological data analysis that promotes topology based on supervised learning techniques also has great potential in its application to scientific visualization. Together with the classification and descriptions of papers, we provide a navigation tool where the surveyed papers are distributed along 2 axes. This tool provides a different viewpoint for the state-of-the-art survey. The first x-axis, single task versus general purpose, specifies whether a specific paper addresses a singular challenge of visualization in astronomy, or whether it describes a more general purpose system that can be applied to a wide array of potential applications. The second y-axis, technique versus application, specifies whether a paper develops a specific visualization or analysis technique, or whether it combines many different techniques to address a specific application. Let's try to embed some of the examples we went through today into this plot. Let's start from the top left quadrant, single task and application. We have the 3D printing of nebulae and the VR system of a star remnant. For the application and general purpose quadrant, we have software such as AstroBlend, Worldwide Telescope, and TopCat. For the general purpose and technique quadrant, we have the X3D pathway example. And for the single task and technique quadrant, we have the cinematic visualization system and the filament reconstruction system, Polyform. Here we have the complete navigation tool. The primary category, data analysis tasks, is double encoded with colors and marker shapes. We lay out the papers in their general areas in the figure to avoid overlap of labels. On the opposite diagonals of the single task and application quadrant and the general purpose and technique quadrant, we see fewer papers, indicating research opportunities in the near future. To make the survey results more accessible and actionable to the research community, all papers surveyed, including associated metadata, can be explored online with a visual literature browser developed with the Surveys framework. We embedded an interactive version of the navigation tool here as well. A major finding of this work is that there remains a significant gap between cutting-edge visualization techniques and astrophysical datasets. We therefore take this opportunity to issue a call to action for both the visualization and astrophysics communities to consider more robust and intentional ways of bridging the gap between visualization methods and astronomy data. We make the specific recommendations below as concrete suggestions for improving this goal over the next decade. We suggest the construction of a comprehensive AstroVis roadmap for bringing these disparate communities and stakeholders together at both the grassroots and institutional levels. In order to build community, we suggest regular annual joint meetings that will explicitly target this gap and bring together visualization and astrophysics domain expertise. To assist in the access to information and literature, we suggest that an AstroVis keyword be added to papers published in either astrophysics journals or visualization publications to make interrogation of papers easy for the communities. We further suggest starting visualization and data challenges within the large publicly available astrophysics data surveys. We are encouraged by the progress that has been made in the last decade, and we look forward to the next decade of development, discovery, and education. Thank you.